Modules and Homological Algebra, Lecture 2, Substructures and Homomorphisms. We start with substructures. Let A be some algebraic structure. For example, it can be a semigroup, a monoid, a group, a ring, a field, or an algebra. Meta definition. A substructure of A is a subset of the underlying set of A which inherits the same kind of structure by restriction. Now let us give some detailed examples of this meta definition. Example 1. If S, dot is a semigroup, then a subsemigroup of S is a non-empty subset T of S such that T is closed with respect to the operation, which means that for any A and B in T, their product A times B belongs to T. Example 2. Assume that M, dot, E is a monoid. A submonoid of M is a subset N of M, which contains the identity element E, and which is closed with respect to the operation on M. In other words, for any A and B in our subset N, their product AB should belong to N. Example 3. If G, dot, E is a group, then a subgroup of G is a subset H of G, which contains the identity element E, which is closed with respect to the operation. In other words, for any A and B in H, their product AB belongs to H, and which is also closed with respect to taking the inverse element, which means that for any element A in H, the inverse A inverse of A should belong to H. Here are concrete examples. The set of all positive integers with respect to addition is a subsemigroup of the set of all non-negative integers with respect to addition, because the sum of two positive integers is positive. Example 2. The set of all powers of 2, so 2 to the power 0, 2 to the power 1, 2 to the power 2, and so on, this set is a submonoid of the monoid of all positive integers with respect to multiplication and with the identity element as the unit. Note that our set of the powers of 2 contains 1 because this is 2 to the power 0. And then if you take 2 to the power I and times 2 to the power j, you get 2 to the power I plus j. Example 3. The set of all even integers is a subgroup of the group of all integers with respect to addition. Indeed, 0 is an even integer, the sum of two even integers is an even integer, and if you have an even integer, its opposite is again an even integer. Example 4. The ring of integers is a subring of the ring of all rational numbers. Example 5. The field of all rational numbers is a subfield of the field of all real numbers. Example 6. So the algebra of real numbers over the rational numbers is a subalgebra of the algebra of all complex numbers, considered as an algebra over the rational numbers. And here is a negative example. The set of all 2 times 2 matrices, let's say with rational coefficients, when embedded into the top left corner into the set of all 3 times 3 matrices, does not form a subalgebra inside 3 times 3 matrices. And the reason for that is that it does not contain the unit matrix, which is the identity element with respect to multiplication. So it's not closed with respect to the unit element. Sometimes these kind of subalgebras are called non-unital subalgebras. Now let us talk about homomorphisms. Let A and B be 2 algebraic structures of the same type. For example, 2 semigroups or 2 algebras. A meta definition. A homomorphism from A to B is a map from the underlying set of A to the underlying set of B, which intertwines all the additional structure which we have on A and B. For example, if S and T are two semigroups, so we use asterisk for the operation on S and the star for the operation on T, then a semigroup homomorphism from S to T is a map F from the set S to the set T such that it intertwines asterisk operation with star. This means that for all A and B in S, F applied to the product A asterisk B should be equal to F of A star F of B. Example 2. If A and B are two K algebras, an algebra homomorphism from the first K algebra A to the second K algebra B is a K linear map F from A to B. So A and B are K algebras, so they are vector spaces over K. A natural notion of a map from A to B should be that of a K linear map. So a homomorphism is a K linear map which intertwines the product. So F applied to A asterisk B should be equal to F of A star F of B. And also it should send the unit element 1A in A to the unit element 1B in B. Remark: in some cases, some requirements for homomorphism might be redundant. For example, if we discuss homomorphisms of groups, then formally we need the requirements that any group homomorphism sends the identity element in the first group to the identity element in the second group. However, this requirement follows from the requirement that our homomorphism F should intertwine the operation in the first group with the operation in the second group. So some of the formal requirements, if you write all of them, they might be redundant. Here are some concrete examples. If B is a substructure of A, then the corresponding embedding of B into A is a homomorphism. This is trivial. Example 2, the determinant map from the multiplicative monoid of all n times n matrices over subfield K to K is a homomorphism of multiplicative monoids. Example 3, if A is a K algebra, then the unit map from K to A, which sends the element x in K to x times the unit element in A, this is a homomorphism of K algebras. Example 4, if R is a transcendent real number, then we have a map from the field of rational functions with rational coefficients for some indeterminate x to R, which is identity on the rational numbers, on the coefficients, and which sends the indeterminate x to our chosen transcendent number R. So this map gives rise to a homomorphism of fields. Another example, if R is any ring and little r is an element in R, then there is a unique homomorphism from the ring of all polynomials with integer coefficients for the indeterminate x to R, which sends the indeterminate x to our element little r. This is very similar to example 4. Example 6, if V is a k-vector space of dimension n and with a fixed basis, bold E, then we have an algebra homomorphism from the algebra of all linear endomorphisms of V to the algebra of all n times n matrices over K. So here n is a dimension of our vector space V. And this is the coordinate map. It sends a linear endomorphism f of V to its matrix with respect to the basis E. Let us now make one remark on various types of homomorphisms. So we have injective, surjective, and bijective maps between sets, and we also have homomorphisms which are called epimorphisms, monomorphisms, and isomorphisms. In general, one should be very careful with using the later terminology, which is a categorical terminology, with respect to homomorphism of algebraic structures, because sometimes it's not equivalent. So here is an example. The claim is that the natural embedding of monoids from the monoid of all non-negative integers with respect to addition into the monoid of all integers with respect to addition. So this later monoid is a group actually, but never mind. This embedding, which is an injective map, but is obviously not a surjective map. So this is not a surjective map, but it is an epimorphism in the category of monoids. Proof? So let F and G be two monoid homomorphisms from the monoid of all integers with respect to addition to some monoid M, asterisk, E. Assume that F and G coincide on all non-negative integers. We claim that F and G are equal. Indeed, if we take a non-negative integer y, then we know that 0 is equal to y plus minus y, and it is equal to minus y plus y. And so if we apply f, we will get that E is equal to f of y asterisk f of minus y, and the same in the opposite order. But this means that f of y is invertible in M, and f of minus y is exactly the inverse of f of y. And similarly, g of minus y is the inverse of g of y. Since the inverse is unique, and we have assumed that f of y is equal to g of y because y is a non-negative integer, we have that f of minus y is equal to f of y inverse, which is g of y inverse because f of y is equal to g of y, and the inverse is unique, and this is equal to g of minus y. So f and g also coincide on minus y. So they coincide on all elements of Z. Next, let us discuss a very specific kind of homomorphism from the very specific semigroup, which we will use later, and this is a free property of the semigroup of all words. Let A be a finite non-empty alphabet, which consists of the letters A1, A2, and so on, AK. Consider the semigroup A cross of all non-empty words in A with respect to concatenation of words. Let S, asterisk be any semigroup. Proposition, which is usually referred to as the free property of our semigroup of words, for any choice of k elements in S, so let's call this bold X, and the elements are x1, x2, and so on, and xk, there is a unique homomorphism phi, bold X, from our semigroup A cross to S, which sends AI to xi for each I. Proof. If we take any word in our alphabet A, so the word AI1, AI2, and so on, AIM, then phi x applied to this word should be equal, due to the property of being a homomorphism, it should be equal to phi x of AI1 asterisk phi x of AI2 and so on phi x of AIM, which is equal to xi1 asterisk xi2 asterisk and so on asterisk xim. So this implies that if phi x exists, then it is unique, because it is uniquely defined on each element in A cross. At the same time, the fact that this formula defines a homomorphism is trivial, and this completes the proof of the proposition. Now let us discuss the notion of the kernel of a homomorphism. Let f from x to y be a homomorphism between two algebraic structures of the same type. Definition: the kernel of f is defined as the equivalence relation tilde with a superscript f on x given by the following. So A is tilde f equivalent to B if and only if f of A is equal to f of B for any A and B in X. Let us note that it is clear from the definitions that tilde upper f is an equivalence relation on X. Here is the first example. If f is injective, then the kernel of f is by definition the equality relation on X. Different elements of X are sent to different elements. Example 2. Consider two monoids M and M tilde, and let F be the map from M to M tilde, which sends all elements in M to the identity element E tilde in M tilde. Then this is obviously a homomorphism, and the kernel of this homomorphism is the full relation on M, because all elements collapse to the identity. Let us now try to connect this with our usual notion of a group homomorphism and the kernel of a group homomorphism. Let F be a group homomorphism from a group G to a group G tilde. Then there is a normal subgroup H in G, and this is what is usually denoted the kernel of F, such that the kernel of F, in our sense, coincides with the equivalence relation on G, which is given as follows. The equivalence classes of this relation are the cosets of G modulo H. Since H is normal, it doesn't matter whether this is a cosets on the left or on the right. Proof. We define H to be the set of all elements X in G which are mapped by F to the identity element E tilde in G tilde. If f of x is equal to f of y, then f of x star y inverse is equal to f of x star tilde f of y inverse, and this is equal to E tilde. So this means that x star y inverse belongs to H. In other words, x belongs to H star y. And by a similar argument, x belongs to y star H. So if f of x is equal to f of y, then x belongs both to the left H coset of y and the right H coset of y. Conversely, if x is equal to H star y, where H is in H, then f of x is equal to f of H star y by definition. By the property of the homomorphism, this is f of H star tilde f of y. F of H is E tilde by definition, so we get E tilde star tilde f of y, which is f of y. And this completes the proof of this proposition. Next, let us discuss congruences on semigroups. Let S be a semigroup. Definition: an equivalence relation tilde on S is called the congruence, provided that for any elements A, B, and C in S, the relation A tilde B implies both AC tilde BC and CA tilde CB. So in other words, the relation tilde should be stable with respect to both right multiplication with elements in S and left multiplication with elements in S. Example 1, the equality relation is a congruence on any semigroup. This is obvious. Example 2, the full relation is a congruence on any semigroup. This is again obvious. Lemma: the kernel of any homomorphism is a congruence. Proof: let F be a semigroup homomorphism from the semigroup S to the semigroup T. If f of A is equal to f of B, then f of AC is equal to f of A times f of C, because f is a homomorphism, but f of A is equal to f of B, so we can write this as f of B times f of C, and again, since f is a homomorphism, we get f of B, C. Similarly, f of CA is equal to f of CB, and this completes the proof of the lemma. So the kernel of any homomorphism between two semigroups is actually a congruence on the domain semigroup. Now let us discuss quotients of semigroups. Let S be a semigroup and tilde a congruence on S. Consider the set S modulo tilde of all equivalence classes of tilde. For S in S, let us denote by S overlined the tilde equivalence class contained in S. For A and B in S, let us set that A overlined times B overlined is equal to the overline of the product A, B. Lemma: this defines on S modulo tilde the structure of the semigroup. Proof: we need to prove that this is well defined. And the associativity, the only axiom, follows directly from the associativity of the multiplication on S. So let's prove that this is well defined. Assume A is tilde equivalent to C and B is tilde equivalent to D. Since tilde is a congruence, we can multiply A equivalent to C on the right with B to get that AB is equivalent to CB. And we can multiply B equivalent to D on the left with C to get that CB is equivalent to CD. Since tilde is an equivalence relation, we conclude that AB is equivalent to CD by transitivity. And so our operation is well defined. It doesn't depend on the choice of representative of a tilde equivalence class. Next, let us talk about the canonical projection. Let S be a semigroup and tilde a congruence on S. Consider the quotient semigroup S modulo tilde. This is usually called the quotient of S modulo tilde. We have the map from S to this quotient of S modulo tilde, which sends an element S in S to its equivalence class under tilde. This map is obviously surjective by definition, and from the definition of the multiplication on our quotient semigroup, it follows that this map is a semigroup homomorphism. This is a map which is called the canonical projection. And by definition, the kernel of this map is the relation tilde. And so we can conclude that each congruence on a semigroup is the kernel of some homomorphism. We already know that the kernel of any homomorphism is a congruence, and now we established that the congruence is a kernel of some homomorphism. So congruences are exactly the kernels of homomorphisms. Now let us describe congruences in groups. Let G be a group and tilde a congruence on G. Claim then there is a normal subgroup H of G such that the equivalence classes of tilde are exactly the cosets of G modulo H. Proof. Define H as the equivalence class of E. If A is equivalent to B, then by multiplying by A inverse on the left, we get that the identity is equivalent to A inverse B, and on the right, we get that the identity is equivalent to B A inverse. In other words, A inverse B and B A inverse belong to H, which means that both A and B belong to the same coset of G modulo H on any side. And by the congruence axiom, each H coset is a subset of some equivalence class of tilde. So this means that each H coset coincides with an equivalence class of tilde, and hence all cosets are both left cosets and right cosets, which means that H is normal. And this completes the proof. Now we can discuss quotients of groups. Let G be a group and tilde a congruence on G. Recall that we just established that there is a normal subgroup H in G such that the equivalence classes of tilde are exactly the cosets of G modulo H. By the semigroup construction, G modulo tilde is a semigroup because G is a semigroup, and if we factor a congruence, we get a semigroup. The class of the identity is, of course, a unit in G modulo tilde. In other words, G is a monoid, and the semigroup quotient of a monoid is a monoid, where the identity is just the class of the original identity. But G is also a group. So if A is an element in G, we have A inverse, its inverse in G, but then the class of A inverse is the inverse of the class of A in the quotient. So the semigroup G modulo tilde is actually a group. So the quotient of any group by any congruence is actually a new group. So this is what is called the quotient of G modulo tilde, or more often the quotient of G modulo H, modulo normal subgroup H. Next, let us move to kernels of ring homomorphisms. Recall that an ideal I of a ring R is an additive subgroup of R, which is stable both with respect to the left and the right multiplication with elements in R. This should be R, not I. Lemma. Let F from R to R tilde be a ring homomorphism. Then there is an ideal I in R, which is usually denoted ker of f and called the kernel of f, such that the kernel of f in our sense coincides with the equivalence relation whose equivalence classes are the additive cosets of R modulo I. Proof: again we set I to be the set of all elements x in R which ascend to the zero element in R tilde. From the group case, we know that I is an additive subgroup of R. So F is a ring homomorphism. In particular, it's a homomorphism of groups. So the kernel is a subgroup of R, and the kernel of F coincides with the equivalence relation whose equivalence classes are the additive cosets of R modulo I. And here we don't need the normality because the additive structure is commutative on any ring. Now for an element A in R and X in I, f applied to Ax is equal to f of A times f of X, which is equal to f of A times 0 tilde, because X is in I, so f of X is 0 tilde, which is equal to the 0 element in R tilde. This means that Ax belongs to I, and similarly Xa belongs to I. That is, I is an ideal. And now we can discuss quotients of rings. Let R be a ring and I an ideal of R. Should be R. The quotient R modulo I of additive R cosets modulo I has, by our above discussion, the natural structure of an additive group. The ideal axiom implies that if we define the product of these cosets in the following way, so if we take the coset containing A and multiply with the coset containing B, we define this as the coset containing the product AB. So similarly to the group case, from the ideal axioms it follows that this is well defined. So this gives us a well-defined binary operation on the quotient. And associativity and the distributivity of this operation with respect to the addition follows directly from the corresponding properties of R. And this means that our quotient becomes a ring. This is usually called the quotient ring of R modulo I. And similarly to the previous cases, we have the canonical projection from R to the quotient, which sends an element R to its equivalence class modulo I. Now let us briefly discuss quotients of fields and algebras. Quotients of fields are very easy, so they are defined exactly in the same way as quotients of rings. However, any field has only two ideals, the zero ideal and the field itself. And this follows from the fact that all non-zero elements in any field have multiplicative inverses. If an ideal contains a non-zero element, by multiplying, we should get all non-zero elements, and then multiplying with 0, we also get 0. So fields have very few ideals, namely at most two, the zero ideal and the field itself. And therefore, any field has only two quotients, the field itself and the singleton field, the field consisting of one element, very degenerate object. In the case of algebras, quotients of algebras are the same thing as quotients of rings. And we only know that an ideal of a K algebra is a K subspace. This is the additional structure which is preserved. Let us now discuss some examples. Example 1. Consider the additive semigroup of all positive integers. For a positive integer k, we have a congruence on this semigroup whose equivalence classes are the singletons 1, 2, and so on k minus 1, and then all other elements connected into one equivalence class. So we have singletons up to some point, and then the rest is a unique equivalence class. It's very easy to check that this is a congruence. And the corresponding quotient of the semigroup of all positive integers with respect to addition modulo this congruence. This is a finite semigroup with k elements and with one generator, which is the element 1. So 1 plus 1 is 2, and so on. If we do it k times, we get this element, and this is a zero element, because if we add this element to anything in this semigroup, we get this big element back. Example 2, for a positive integer k, we have the ideal in the ring of all integers, which consists of all integers divisible by k. We can take the corresponding quotient, and this is exactly the finite arithmetic ring z sub k, which appears in the elementary number theory. Example 3, let Q be a quiver and K a field. Then we have the corresponding path algebra of this quiver Q over K. For any ideal I in this path algebra, we have the corresponding quotient of KQ modulo I. And this is what one usually calls the algebra given by a quiver and relations. So this quotient is given by the quiver Q and any set of relations which generate the ideal I. Let us finish with some problems and questions. Question 1. Give precise definitions for subrings, subfields, and subalgebras. Question 2. Construct further examples of non-surjective epimorphisms between some algebraic structures of the same type. Question 3. Check all details in the proof of existence for the free property of A cross. Question 4. Explain with all details why an ideal of a K algebra is a K subspace. And question 5, let R be a ring. Assumes that the only ideals of R are 0 and R. Does this imply that R is a field? Thank you very much and see you next time.